Good evening. This is Math 2414. It's March 28th. A couple of announcements to start off lecture today. First of all, Exam 2 grades will be posted by April the 4th. That's next Wednesday. So within the next week, they'll be posted. So I still don't have all the exams in my possession yet. Gradually, I'll be doing that over the next day or two. And so the grades will be posted about a week from today, within a week. I will send a remind message to tell you that I have posted the grades, and you can look at your grades at that point. I'll give you an update on how the grading is going on April the 2nd, next Monday, for next Monday's lecture. Homework. You will have homework due on April the 2nd. I will assign that at the end of lecture today. So that will be assigned at the end of lecture. Signed at the end of lecture. Today. Online office hours. I haven't reminded you of this recently, but remember that I always have online office hours, and I'll be resuming the regular hours now that we're out of the testing window. Tuesday, Wednesday, and Thursday from 11 to noon. And then on Tuesday and Sunday from 8:30 to 9:30 p.m. All right, and then today, what we are going to do is we're talking about polar coordinates last time, and so what we will do today is we will continue our discussion of polar coordinates, and we will be looking at finding dy dx given a polar curve, looking at horizontal and vertical tangent lines given a polar equation, and then we'll look at arc length and area inside a polar curve. So we have lots to do today, and so we'll go ahead and get started. Let me pause the video just for a second here. All right, so let's go ahead and get started. So first thing is finding dy dx given a polar curve. And so let me go ahead, and I'm going to go back to these graphs in a minute. So let me go ahead and just get a blank page started here. So what we're doing is, first of all, finding dy dx given a polar curve in the form r equals some function of theta. And all this involves is using the parametric form of the derivative, that dy dx would be equal to, if y and x are represented parametrically, would be equal to dy dt divided by dx dt. Right? We saw that when we were dealing with parametric equations earlier in the chapter. So what we do is we take our polar curve. So let's say we are given the polar curve r equals 1 plus 2 cosine theta. We use the idea that x is equal to r cosine theta and y is equal to r sine theta. Right? Remember, that's the parametric form of polar coordinates. And we simply substitute the r value in. So you get x is equal to 1 plus 2 cosine theta times cosine theta. There's a 1 stuck in there. And then y is equal to 1 plus 2 cosine theta times sine theta. And then you simply find dy dx. Now you've got x and y expressed in terms of the parameter theta. So dy dx would be equal to dy d theta divided by dx d theta. And this is how you can find dy dx if you're given a polar curve. So you need the parametric form of polar coordinates, and then you're just substituting in the r value there, and then you've got the parametric equations that you need. So dy d theta, I'm going to leave them in factored form. So this would be the first factor, 1 plus 2 cosine theta, times the derivative of the second factor, which would be cosine theta, plus the second factor, sine theta, and I'm going to write it over here, times the derivative of the first factor. Derivative of 1 is 0. Derivative of 2 cosine theta would be negative 2 sine theta. So that would be the numerator. By the way, a little word of caution here. You frequently, with these kinds of problems, end up with nasty expressions, just so you know. Dx d theta, use the product rule again, so that would be 1 plus 2 cosine theta, first factor, times the derivative of the second factor, which would be negative sine theta, plus the second factor, which is cosine theta, times the derivative of the first factor, which would be the same, negative 2 sine theta, just like it was in the numerator. And then you simplify. And what I'm going to do here is I'm just going to say now simplify, and I'm just going to leave that at this point. I just wanted to review how you actually found a derivative, okay? And so now what we're going to do is we're going to tackle a problem where we're actually looking for horizontal and vertical tangent lines. And this can be messy in polar coordinates, quite frankly. So let's have a look at that. So I'm going to go ahead and start a fresh page. So let's say we have this polar equation. We're going to do something fairly simple. R equals 4 cosine theta. And I want to find all points of vertical or horizontal tangency. Now, I don't know if you remember this from last time, but r equals 4 cosine theta is a circle that passes through the pole. This is a circle passing through the pole. With a diameter of 4. All right, so if you wanted to sketch it, you certainly could do that. So a diameter of 4, I'm going to go over here 4 units, go up 2 and down 2, passes through the pole. And so this is our graph. So horizontal and vertical tangents are pretty obvious from the graph. So let's go ahead and use the calculus to find these. That's what we're practicing here. All right, so remember what we're going to need to do first of all in a problem like this is first find dy d theta and dx d theta, right? Because we're going to, we know that that's how we're going to find horizontal and vertical tangents here. So first find dy d theta and dx d theta. All right, so we know that x is equal to r cosine theta, and so that means that x is equal to r, is equal to 4 cosine theta times cosine theta. So x is equal to 4 cosine squared theta. Y is equal to r sine theta. And so y would be equal to r, we know is 4 cosine theta, so this would be 4 cosine theta times sine theta. And that really, you know, we could leave it like that. It doesn't really simplify too much beyond that, the way I would look at it. All right, so dx d theta, dx d theta in our problem, derivative of x with respect to theta, would be the chain rule. And so you'd have 8 cosine theta times, that's the derivative of the outside function, the square function, times the derivative of the inside function, which would be negative sine theta. So dx d theta would be equal to negative 8 cosine theta sine theta. All right, and then dy d theta would be equal to, this would be a product rule problem. it'd be 4 cosine theta. I'll use that as my first factor, times the derivative of sine theta, which is cosine theta, plus, and then, so that's the first times the derivative of the second, and be plus the second times the derivative of the first, which is going to be negative 4 sine theta, and that would be times sine theta. So dy d theta here would be equal to 4 cosine squared theta minus 4 sine squared theta. All right, and there's several ways that we'll be able to deal with that equation, depending on how you want to deal with this. One way would be to factor out a 4, and that would leave you with cosine squared theta minus sine squared theta. Now remember, that's not the Pythagorean identity. Pythagorean identity is cosine squared plus sine squared. So this is dy d theta is equal to 4, but this is the double angle for cosine. The cosine of 2 theta is the same thing as cosine squared minus sine squared. It's a handy identity to know. All right, so if we're looking for horizontal tangent lines, let me go ahead and put this in a different color so it kind of stands out a little bit. So horizontal tangent lines, recall that that's where, with respect to the parameter, that y stops changing. And so the horizontal tangents would be where dy d theta is equal to 0. So what we do is we set 4 cosine of 2 theta equal to 0, which gives us cosine of 2 theta equals 0. And then so that would be when cosine is 0 when the angle is pi over 2 and 3 pi over 2 and so on. And so theta would be pi over 4 and 3 pi over 4 and so on. So when theta is pi over 4, 3 pi over 4, etc., you're going to get horizontal tangent lines. All right, and so the horizontal tangent lines are going to be at pi over 4. Theta is equal to pi over 4. And so notice that in our problem right here, that would be this angle right here. That's at theta equals pi over 4. And that makes sense that when theta is equal to pi over 4, sure enough, you're going to get that point right there. And that point is going to give us the place where there's a horizontal tangent line. And then 3 pi over 4, well, here's theta equals 3 pi over 4 over here. And here the r value is going to be negative, and so you get this point right here. And so that would be when theta is equal to 3 pi over 4 right there. All right, and then you could find the r value from the equations. And so if you find the r value there, right, you know that r is equal to 4 cosine theta. So r is equal to 4 cosine theta. And so you get that r would be 4 times cosine of pi over 4. And so it'd be 4 times the square root of 2 over 2, or 2 square root of 2. Right, and so the point here would be the point 2 square root of 2 pi over 4. Like that. And then if you use 3 pi over 4, this would be one representation for the other point here, you're going to end up just with a negative here, and this is going to be negative 2 square root of 2, 3 pi over 4. And that would be this point right here. Those would be the polar coordinates for that point. These would be the polar coordinates for this point right here. And then obviously you could go ahead and convert those if you wanted to rectangular coordinates. The rectangular coordinates are easy to read. It's just going to be 2, 2 for the first point, and 2, negative 2 for the second point. All right, so those are the horizontal tangents. All right, the vertical tangents. I think I have maybe enough room here. Vertical tangents are when there is no motion in the x direction. So this would be when dx d theta is equal to 0. So let's see. So dx d theta is equal to negative 8 cosine theta sine theta. So you have negative 8 cosine theta sine theta is equal to 0, which gives you the cosine of theta 0 or sine of theta is equal to 0. So when cosine of theta is equal to 0, you get theta to be pi over 2 and 3 pi over 2, and etc. Right? And when sine of theta is equal to 0 at 0 and at pi, and so on. So now pi over 2 and 3 pi over 2, right? Those values, like theta equals pi over 2, is going to give you actually the pole here. And you're going to have, when theta is pi over 2, you get that r is 4 cosine of pi over 2, which is just 0. And so you get the point where r is 0 and theta is pi over 2. You have 0 pi over 2, and that's the pole. That's just one name for the pole, like that. All right, and then when theta is equal to, for example, 0, you're going to get this point right here, because you're going to get r to be 4 cosine of 0. So r would be equal to 4, because cosine of 0 is 1. And so that would be this point right here. R is 4, theta is 0. And that's the polar form for that point right there. One version of it, at least. You know, if you use pi, you end up with another version of that same point. You end up with negative 4 pi, which is just another version of this point right here. Remember, polar coordinates, infinite representations for each individual point like that. All right, so that is an example of finding horizontal and vertical tangents to a polar curve. So I wanted to kind of go over that and make sure that there were no questions there and that you're okay with that. We did talk about that with parametric equations also. All right, and so now what we're going to do is we're going to move on and we're going to talk about arc length and area. Arc length is relatively straightforward. Area can be complicated geometrically, and we're going to spend a lot of time with area bounded by a polar curve. So arc length given a polar curve in the form r equals some function of theta. Okay? So now if you recall for arc length that if you're given y to be a function of x, in other words, this is going to be the rectangular form for arc length. We've done that before in class. This is called the rectangular form. So y is just some function of x. Then the arc length integral is the integral from a to b of the square root of 1 plus the square of dy dx. That's if y is a function of x. And if x is a function of y, you just change up the derivative so that it's with respect to x. So that's the rectangular form for arc length. And then we have the parametric form, which we've also talked about. The parametric form is if you're given that x is some function of t and y is some other function of t. In other words, x and y are expressed parametrically. And when you're given an equation like that, or set of equations like that, then the arc length would be the integral from one parameter value to the next, from t1 to t2, of the square root of dx dt squared plus dy dt, quantity squared dt. Right, and so this is the parametric form for arc length. Remember that, you know, in rectangular form, the limits of integration are x values here. Right, those are x values. In parametric form, these are parameter values. Right, you're integrating with respect to t right here. So those would be the limits of integration. Right, those are the values of t. All right, that define the piece of the curve that you're talking about. So finally, we have the polar form for arc length. And what you do is you use our parametric equations, x equals r cosine theta and y is equal to r sine theta. Right? Remember, that's the parametric form for polar coordinates. And so you use those forms in the parametric equation form for arc length. And when you do that, and I'm going to kind of skip over the algebra here, but what you're doing is you're taking these values and you're substituting them into the form that we got just above here. Right, so you're going to substitute them into this form. In other words, you're going to find dx dt squared and dy dt squared. So you're going to substitute here. And when you do that, you end up with this polar form. You end up with the polar form, this integral, the integral from theta 1 to theta 2. So these are values of the angle theta. And this would be the square root of r squared plus dr d theta quantity squared d theta. Right, and these are obviously the limits of integration now are theta values, values of the angle that define the curve that you're talking about. All right, so now we have three separate forms for arc length. Now they're all equivalent. It just depends on what they're all based on length, and the distance formula actually. But it depends on what you're starting with in each case as to which form you use. Whether you're starting with a function where y is a function of x, where x and y are defined parametrically, or if you're given a polar form where you're starting with, and I didn't ever write this, but you're starting with the form that r is equal to some function of theta. Right? That's what you're starting with there. All right. So let's go ahead and look at some examples of how we would go about doing this, using this form. All right, so we are going to find, so here's an example. We're going to find the length of the curve given by r is equal to 8 plus 8 cosine theta, or r is equal to 8 times 1 plus cosine theta. And in that form, you can identify that this graph is a cardioid, and it's symmetric with the x-axis because this is a function of cosine only. So it's a symmetric with the x-axis. All right, so this cardioid, we're going to not draw this out to scale because of the 8. It's pretty big out there, but this cardioid comes out here when theta is 0, and it's out here at 16, 0. Right? And then the graph when theta is pi over 2, then this would be at 8, and so that would be 8 on our scale right here. And so you get this cardioid kind of looks like this. Now you really wouldn't necessarily need this graph, but it's not a bad idea to have. And the last part of that cardioid is kind of ugly, the way I drew it, but it's not a whole lot better, but at least a little bit better. So there's our cardioid right there. Right, and so we want to find the length of this curve. All right, so we know, and I'm going to go to a different color here because that's the setup there, that the arc length integral then is the integral from theta 1 to theta 2 of the square root of r squared plus dr d theta quantity squared d theta. All right, so we need to find the little pieces to this particular equation, right? So first of all, r squared. You know, if you know that r is equal to 8 plus 8 cosine theta, then r squared would be, and I'm going to square the factored version here, the 8 times 1 plus cosine of theta. That's probably a little bit easier. So r squared would be equal to 64 times 1 plus cosine theta quantity squared. Right, and I'm going to go ahead and multiply this out because we're going to probably want to simplify. So this would be 64 times 1 plus 2 cosine theta plus cosine squared theta. And then multiply through there, and you have 64 plus 128 cosine theta plus 64 cosine squared theta. So that's r squared. And then dr d theta, dr d theta, the derivative of r with respect to theta would just be negative 8 sine theta. So this is a lot easier, luckily. Dr d theta quantity squared would be 64 sine squared theta. So those are the two pieces to my integral as far as the pieces that are underneath the radical here. All right, so our arc length integral here would become, we trace out one full length of this curve from 0 to 2 pi. So we're going to integrate from 0 to 2 pi. And this would be the square root of r squared, which is 64 plus 128 cosine theta plus 64 cosine squared theta. And that would be plus 64 sine squared theta. Now notice there's, if you're observant here, there's quite a bit of simplifying that we can do here. You have the square root of 64 plus 128 cosine theta. And those last two terms I factor out as 64, and I'm left with cosine squared theta plus sine squared theta. And that is 1. And so that just leaves me with a 64 right there. And so this simplifies quite a bit. You end up with the square root of 128 plus 128 cosine theta d theta. And I forgot to write the d theta there. I need to write that, definitely. And so now I could factor out 128, but I'm not going to do that. I'm just going to factor out a 64, since I know the square root is 64. So I take out a 64 here. That's 64, and this leaves me with 2 plus 2 cosine theta. And then the square root of 64 is 8. So you end up with 8 times the integral from 0 to 2 pi of the square root of 2 plus 2 cosine theta d theta. And then you can factor out a square root of 2 there. And you have 8 square root of 2 times the integral from 0 to 2 pi of the square root of 1 plus cosine theta d theta. Now let me show you a trick, sort of, to evaluate the square root, or to change the form of that square root of 1 plus cosine theta, because that is not really a form that we have anything for as far as integration goes. And so the question is, how do you deal with that? And so what I'm going to do here is I'm going to show you a little trick that you can use here, and you're going to want to know this possibly for the test. Cosine squared theta, first of all, remember, we know is 1 plus cosine 2 theta divided by 2, right? That's an identity we had from the last chapter. So this is 2 cosine squared theta equals 1 plus cosine of 2 theta, like that. And so what I want you to do is look at the angles. So the angles here are theta and 2 theta. So if you just substitute, you're saying that the angle on one side, on the left side, is half of the angle on the right side. So if I wrote this as 1 plus cosine of theta over here, then this side, the left side, would be 2 cosine squared of theta over 2, because it's half. The angle on the left side is half the angle on the right side. And so what you have here is that, notice in our integral, is we can make that little substitution, and instead of writing 1 plus cosine theta, we can write 2 cosine squared of theta over 2. That's a trick. I'll tell you that right now. That's a trick, but it's a nice trick to know here, definitely. So this would be 8 square root of 2 times the integral from 0 to 2 pi, like that. And then instead of the square root of 1 plus cosine theta, we have the square root of cosine of 2 cosine squared of theta over 2. And notice I can take out a square root of 2 from underneath the radical there. And that square root of 2 would multiply by the square root of 2 that's already out in front. And so you have s is equal to 8 times the square root of 2 times another square root of 2 times the integral from 0 to 2 pi of the square root of cosine squared theta over 2 d theta. Now this is where you need to be super, super careful, because the tendency for students is to say, hey, this is just cosine of theta over 2. But that's only true here if, the square root of cosine squared of theta over 2 is equal to cosine of theta only over 2, only if you know that the cosine of theta over 2 is positive. That statement is only true for square roots if the expression underneath the square root is positive. And see, look, the integral here is going from 0 to 2 pi. And as you go from 0 to 2 pi, well, theta over 2 goes from 0 to pi. And cosine is not always positive in that interval from 0 to pi. And so here's where we use a little bit more trickiness here in some ways, is that now we only find the integral, or we only find the length of half of this curve. Notice we have symmetry here. And so if you look at my curve, notice how I highlighted half of it. If I integrate from 0 to pi over 2, I'm sorry, from not 0 to pi over 2, from 0 to pi, then it is guaranteed that, first of all, that would give me half of the length I need, but also it would be guaranteed that the cosine of theta over 2 would always be positive. All right, let me write that down here. That when theta is between 0 and pi, then it's guaranteed that the cosine of theta over 2 has to be positive. And then if that's true, then you can say that the cosine squared of theta over 2 is equal just to the cosine of theta over 2. All right, so now I know that's tricky, but let me copy that last little part down here, and we're going to carry that over to the next page. I'm going to copy that. I'm going to go to the next page. I'm going to paste that in. Paste that up here. So we know that if we're going to only go from 0 to pi, and what's that going to do to my integral? That's going to mean I am going to integrate just from 0 to pi, but then I'm going to need to multiply the integral that I had by 2. So you've got, notice that 8 times the square root of 2 times the square root of 2 is 16, right? So this is, well, let me go ahead and write this. This is 8 times the square root of 2 times the square root of 2 times another 2. And that last 2 comes from the fact that I'm going to only integrate from 0 to pi in this problem, and not from 0 to 2 pi. Makes sense. I'm defining half the length, so I multiply by 2. And now this is just cosine of theta over 2 d theta. And we've turned it into a super easy integral. This is 32 times the integral from 0 to pi of cosine of theta over 2 d theta, like that. All right, so the antiderivative there for cosine of theta over 2 is sine of theta over 2 times the reciprocal of the coefficient of the theta. So that's just a 2 there. And then we have this 32 sitting in front. And this would go from 0 to pi. And so you end up with 64 times the sine of pi over 2 minus 64 times the sine of 0, which is just 64. That's the length of the curve right there, 64. It's 64 units long. All right, so now I'm going to flip the screen back. This trick that I used right here, and I'm telling you right now, it's a trick that I'm highlighting over here at the side. This is a helpful trick to know, that if you have, whoops, I don't need to highlight it twice there. Let me try that again. There we go. That when you have something in this form, the square root of 1 plus cosine theta, that you can use that identity to replace 1 plus cosine theta with 2 cosine squared of theta over 2. And then if you adjust the limits of integration, you can be assured that the cosine of theta over 2 is always going to be positive. And so I adjusted the limits of integration to be able to do that there. All right, so it's a little bit tricky. There's no question about that, but it is something that you can deal with, I think. And you're going to need to know that trick on exam 3. I'll tell you that definitely right now. All right, so that is an arc length question, and rather than going right on to area, let's deal with another arc length question here. So let's go to a different color here. So arc length question number 2. Here's our example that we've got r is equal to secant of theta. That's our polar equation. And in this case, theta is bounded by 0 and pi over 3, like so. All right, and if you look at the the rectangular form for r equals secant theta, you get r is equal to 1 over cosine theta. So you get r cosine theta equals 1, but r cosine theta is just equal to x. This is x equals 1. And so this is a vertical line, is what we have here, right? It's just a vertical line, x equals 1, as theta goes from 0 to pi over 3. On a curve, or if you're going to actually sketch that, this is what you're talking about here. Let's say that this is 1 right here. When theta is 0, when theta is equal to 0, you're right here. And you get this point right here on the curve. When theta is equal to, let's say, pi over 4, you get this point on the curve. When theta is pi over 3 over here, let's say that that's pi over 3, theta equals pi over 3, you're still getting, and let me go ahead and erase that part so I can see it a little bit better. Theta equals pi over 3 looks like this, and you're still getting this line right here, and here's theta equals pi over 3. And so notice you are getting a vertical line, and what we're looking for here is simply the length of this vertical line that stretches from 0 to pi over 3. It's just that piece that I've put in that's solid right there. All right, so that's what we're trying to find the length of. All right, so when we do that, right, we've got the, we know we've got this polar form for arc length, right, that arc length is the integral from theta 1 to theta 2 of the square root of r squared plus dr d theta squared d theta. Now this one won't be as bad as the last one. R squared, first of all, is just secant squared theta. And then dr d theta is secant theta tangent theta. That's not bad. And dr d theta quantity squared is secant squared theta tangent squared theta. And so our arc length integral becomes, arc length is equal to the integral from 0 to pi over 3, because those were the limits we were given, times the square root of r squared, which is just secant squared theta, plus dr d theta squared, which is secant squared theta tangent squared theta. That's all under the radical, and then I'm going to squeeze in my d theta here at the end, d theta. And what happens, this ends up working out fairly nice, because you have the integral from 0 to pi over 3. I can factor out a secant squared underneath the radical. And that leaves me with 1 plus tangent squared theta, d theta, like that. And so 1 plus tangent squared is equal to secant squared. And so you end up with the integral from 0 to pi over 3 of secant to the 4 theta d theta. And see, the integral of secant is positive from 0 to pi over 3. So this is definitely the case, right? Secant of theta is definitely positive in this integral on the interval from 0 to pi over 3, because that's all quadrant 1 angles. And so this is definitely the case that this is just the integral from 0 to pi over 3 of secant squared theta. And boom, that's actually easy, because we know the antiderivative of secant squared is tangent. And so you just end up with tangent theta from 0 to pi over 3. And at the upper limit, the tangent of pi over 3 is simply the square root of 3, tangent of 0. So you have tangent of pi over 3, that's a tangent there, minus tangent of 0, and that's just the square root of 3. And so that's the length of that vertical line from theta equals 0 to theta equals pi over 3. It's just square root of 3 units long. About 1.7 units long. And notice it does agree with my graph on the scale, because that's a 1 right there, and that's a 2. And so 1.7 approximately would make sense for that particular graph. Okay, so that's another arc length problem. So we've worked through 2 arc length problems. Notice that with arc length, because you're dealing with square roots, you're frequently dealing with square roots of things that are squared. So you have to watch for when you can take square roots of things that are squared, and write them out easily. And you have to ensure that the expression is positive when you do that. So you have to really watch for that. All right. So arc length is done, right? We've got, so we're doing good. We found derivatives of polar curves. We found vertical and horizontal tangents on polar curves. And now we've done arc length on polar curves. And so we're going to finish the day by looking at area bounded by a polar curve. So what I want you to do is I want you to think about what you did back as a Calculus 1 student. As a Calculus 1 student, when you were given that y was some function of x, and you were looking for area underneath a curve like that, remember the idea here was to increment the domain a little bit and look at a rectangle that was determined by that little increment like that. So if you recall, you took an x sub I minus 1 and an x sub I, right? And you took that width right there, which was delta x sub I, right? And that was the width of this rectangle. So that was delta x sub I right there. And what did you do? You found the, you approximated the area by looking at the rectangle, the area of that rectangle. And this height of this was f of x, or approximated at least by f of x sub I. That'd be one way to look at it. So the area of that ith rectangle is approximately f of x sub I, a function value, in other words, times the change in the domain value, right? And so, you kind of went through that process, and you ended up with the limit of a Riemann sum, and you could first approximate the area underneath the curve and then actually find the exact area by taking a limit. We do exactly the same thing in polar coordinates, but we are given a function in a different form now. So we're given a polar curve, and so we're given that r is some function of theta, right? And so we've got this curve. So here we'll say is our curve r equals some function of theta right here. And let's say we want to find the area bounded by that theta value right there. We'll call that theta sub 0, and we'll call that alpha, our angle alpha. This is another angle right here. We'll call that theta sub n, and we'll call that angle beta. So we're going to find the area bounded between those two values, just like up at the top where we found the area bounded between two domain values, A and B. We're doing the same thing here. The domain values would be theta, would be alpha and beta, basically. Those would be the angle values. Now, so what are we trying to do? We're trying to find the area of this kind of almost wedgy-looking thing right here, right? That's bounded by our polar curve. Bounded by the polar curve between two domain values. What I want you to do is notice that this is really exactly the same thing as you were doing in Cal 1. Right, in Cal 1, you had two domain values, A and B, and you were finding the area bounded by the curve between those two domain values, right? It's just that the kind of curve we're talking about is different in these two situations, but we're really doing the same thing. So what do we do in the rectangular form? Well, we incremented, we took a little increment of the domain. We call that delta x sub I. Well, we do exactly the same thing here in polar coordinates, is we increment the domain. We take a little slice of that domain, and I'm going to make it bigger than it needs to be here, certainly. Let's say, looks like this. And this would be, this angle would be theta sub I minus 1, and this would be theta sub I. And then we might use the theta sub I value, right? And we actually, we go ahead and I'm going to erase that and make it look a little bit better. It's actually kind of an arc here. And we're actually producing kind of a wedge right there. That's actually a sector, what we call a sector of a circle. That's a sector of a circle that we've just produced there. And the R value there, the radius of that circle would be R sub I, right? And that's, in this case, given by the second value, the theta sub I, that is going to give us R sub I, right? So R sub I is equal to F of theta sub I right here. And that would be the radius of that sector of a circle. Now, I don't know if you remember this, but the area of a sector of a circle, right, if you have, and this is from trigonometry, it's probably been a while since you've talked about this, but this, if you have a circle, let me just draw a circle out right here. The area of a sector of a circle, so here's a sector of a circle like this. The area of a sector of a circle from trigonometry is equal to, area is equal to 1/2 r squared theta. It's equal to the square of the radius times the central angle here, which is, that's theta right there. So our central angle here would be this angle right in here on our picture, and that would be delta theta sub I. That's the width of that, or not the width, but the angle, that's the central angle of that ith little sector right there. And so the area, in this case, for that little sector would be 1/2 times f of theta sub I quantity squared times delta theta sub I. Or we could abbreviate that as 1/2 times r sub I squared delta theta sub I. Right? And that would be the area, the approximate area of the ith sector. So this is the approximate area of the ith sector. So what do? We do exactly the same thing we did back in Cal 1. We take all those little sectors and we add them up, and we find the areas of all those little sectors. We add them all together, and then we let the number of sectors become arbitrarily large. So we let it become arbitrarily large by taking the the limit as the n here, this theta sub n, goes to infinity. And we'll end up with a Riemann sum is what we end up with. And we're taking the limit of a Riemann sum, and we end up with an integral. So dot, 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 we're going to skip over that part of it, but I wanted to show you certainly where this form came from. And so we end up with the integral from alpha to beta of 1/2 r squared d theta. It's a very simple form. That form right there gives us the area inside a polar curve where you've got r to be some function of theta. Right, so it ends up being a really nice form. The one good thing here is because it's 1/2 r squared, we don't really have to be concerned too much with whether r is positive or negative. If you remember the rectangular form at the top of this screen right here, that what we had to do is we could only find the area bounded by a curve. We could only find an area directly that was bounded by a curve that was above the x-axis. We had to kind of deal with the integral a little bit and the signs of the integral if the region went below the x-axis. Well, with polar curves, we don't have that concern because this quantity is always going to be positive. So that ends up working out really nicely in our favor here. All right, so what we're going to do is spend the rest of lecture here talking about some examples where we're using this formula that we've just kind of done a informal derivation of. Definitely not a formal derivation, but an informal derivation for this. So what we're going to do now is look at some examples of area. Examples of area. We're going to start off with a pretty simple one, and we're going to be looking at some relatively complicated ones by the end. All right, so example. Find the area enclosed by r equals 4 cosine theta. Right? And we actually talked about this curve earlier in class today. So 4 cosine theta we know is this circle diameter of 4 that passes through the pole. So, we're trying to find the area of this. The diameter is 4, so the radius we know is 2. And so, we know the area has got to be pi r squared. So this is just going to be pi times 2 squared, or 4 pi. We better get 4 pi as the answer here when we do this problem. All right, so what do we know here? We know that the area would be the integral. Be careful, this circle is traced out twice from 0 to 2 pi. So to find the area here, we simply integrate from 0 to pi. Remember, a circle is traced out twice. Circle is traced out twice. Going from theta equals 0 to theta equals 2 pi. So we would be finding twice the area if we integrated from 0 to 2 pi. So you have to be really careful on polar curves as what range on the angles you have to use for the particular polar curve you're talking about. For circles that go through the pole like this, they're traced out twice from 0 to 2 pi. So we integrate from 0 to pi, and we have our formula, 1/2 r squared d theta. So this is actually easier than the arc length problems we were just doing. This is just 1/2 times r squared. So this is 1/2 times 4 cosine theta squared d theta. Really nice, really easy. So that would be area is equal to the integral from 0 to pi of 1/2 times 16 cosine squared theta, d theta. And so that gives me an 8 on the outside. This is not bad at all. And you have cosine squared. And then remember, this is where our identity comes into play that we talked about back in the last chapter. So this would be 1 plus cosine of 2 theta over 2 d theta. So you take out the 1/2, and so that gives me the area to be 4 times the integral from 0 to pi of 1 plus cosine of 2 theta d theta. Easy, easy integral. So you end up with theta, the antiderivative to be theta plus 1/2 sine of 2 theta. And that would go from 0 to pi. The upper limit would be 4 times pi. And then the sine of 2 pi is 0. So that's just 1/2 times 0. And at the lower limit, the whole thing is 0. And boom, what do we get? We get 4 pi. Yay. So we know that that checks what we talked about earlier, right? That the area better be 4 pi square units here. So that works out pretty nicely. All right, so move on to the next example. So that's a pretty straightforward example here. All right, the next example is just tedious more than anything else. This is the area inside r equals 1 minus sine theta. Now, r equals 1 minus sine theta is a cardioid. And it's a cardioid symmetric with respect to the y-axis because this is just a function of sine theta only. And what you'll notice here is that when theta is 3 pi over 2, that r is 2. When theta is 0, r is 1. And when theta is pi, r is 1. You get a cardioid that has this shape. Something like that, right? And so we're trying to find the area bounded inside that cardioid, right? This is what we're trying to find here, area inside this thing. Okay, so let's look at this problem. So we write down our integral. Area is equal to the integral from, in this case, the cardioid is traced out from 0 to 2 pi. And so you go from 0 to 2 pi, and this is going to be 1/2 times r squared d theta. So this is the integral from 0 to 2 pi of 1/2 times 1 minus sine theta squared d theta. 1/2 r squared d theta. All right, so now it's just a matter of evaluating that integral. So you go from 0 to 2 pi. I could take the 1/2 outside the integral if I want, and this is 1 minus 2 sine theta plus sine squared theta d theta, like that. So this is definitely not too bad. You have to be careful here in that I'm not going to integrate any of this until I'm ready to integrate all of it. So the 1 minus 2 sine theta is no big deal. I can find the antiderivative there. But that sine squared, I need to replace that with my identity of 1 minus cosine of 2 theta over 2. So you got to do that. And then you can go ahead and collect like terms and everything. And so what I'm going to do here is I'm going to do dot, dot, dot in the interest of time. And so this is the integral, 1/2 the integral from 0 to 2 pi of 3/2 minus 2 sine theta minus 1/2 cosine of 2 theta. And I want you to see if you can figure out the dot, dot, dot part, how I went from one step to the next, like that. And then that is not a hard antiderivative there. And you end up with 3 pi over 2. And more dot, dot, dots there in that I want to go on to other problems. And so I'm going to leave those details for you. Right? But that's pretty straightforward as we're going along through that kind of a problem. All right. So now I'm going to go to maybe looking at something that's a little bit more challenging. So let's look at the next problem, and I already have this graph here. This is our problem right here, the curve. Let me go ahead and actually erase a little bit of this So we get a little bit more room on our screen. I'm going to erase part of this. Notice we have a rose curve here. And I'm going to go ahead and move this vertically, just so we have a little bit more room. There we go. So this curve is r equals 2 cosine of 3 theta. Now the cosine of 3 theta is, or the 2 cosine of 3 theta is a rose curve. This is a rose. And if you think about theta being equal to 0, when theta is 0, you get r to be 2. And this rose curve actually, if you look at the orientation, actually looks like I've got it on the screen here with the arrows. And the curve starts here. It starts when theta is 0, right? Theta is equal to 0 right here. And then when theta is pi over 3, you're at the pole. And that's actually important information for us, is that when theta is pi over 3, we're at the pole. So the graph starts off at when theta is 0, you're at the point 2, 0 there. And then you go through 0, pi over 3, and then the graph can go smoothly through that curve, and the orientation looks like this. Right, this is how the graph gets traced out as you're going from 0 to 2 pi. All right, so what we need to do is, what we're going to try to do is find the area enclosed by one loop or one petal of this rose curve. So find the area enclosed by one loop of the rose. So what I'm going to do is I'm going to find, there's a couple of ways you could do this, but I want to talk about tangents at the pole in particular with this problem, and so that's why I'm electing to do the problem the way I'm doing it. Here, so I want to show you some stuff about tangents at the pole. So this is what we're trying to find the area of, is that loop right there. All right, and so if you recall that you find tangents at the pole by setting r equal to 0. We talked about that in the last lecture. So if you set r equal to 0 on my polar curve, you get that equation. So you get cosine of 3 theta equals 0. And cosine is 0 when theta is, when the angle, the cosine, the cosine of what angle is equal to 0, and that would be pi over 2. And then 3 pi over 2, and so on. So that would be 3 theta, and so theta would be pi over 6, and then pi over 2, and so on. So what ends up happening here is you get a tangent at the pole here on my curve. It's a tangent line that passes through the pole right here, and that is at theta equals pi over 6. And actually, this symmetric tangent at the pole is at theta equals negative pi over 6. So in this particular problem, you could actually do this, set up this integral several different ways. So several ways, I'm going to put that in quotes, to integrate on this problem. First of all, what you could do is you could do the integral from negative pi over 6 to pi over 6. That's one way to do this. Another way, or you could integrate from 0 to pi over 6 and multiply by 2. That would be another way you could do this integral. You could also integrate, let's see, so that's pi over, and you could integrate just from 0 to pi, which 0 to pi traces out the entire rows in this case. If you think about it, if you go from negative pi over 6 to pi over 6, that's just pi over 3 units total right there. This is pi over 3 total radians right here, I should say, not units, but radians. That angle is pi over 3 right there, and that traces out one loop. So each loop is traced out over pi over 3 radians, pi radians altogether. So you can integrate from 0 to pi and multiply by 1/3. All those would be ways that you could set up this integral. All right, so I'm going to use, so we've got our integral, first of all, from alpha to beta of 1/2 r squared d theta. That's our general form for area. And I'm going to use the second way here. I'm going to multiply by 2 and integrate from 0 to pi over 6. And this would be 1/2 times 2 cosine of 3 theta quantity squared d theta. All right, so you end up with a 4 there. So you end up with the area to be 4 times the integral from 0 to pi over 6 of cosine squared of 3 theta. And then here's where you'd use our identity again, and you'd have area to be the integral, or 4 times the integral from 0 to pi over 6 of 1 plus cosine of 6 theta, because it's a double angle identity, over 2 d theta, like that. And so this actually works out fairly nicely here. This is the 2 times the integral from 0 to pi over 6 of 1 plus cosine of 6 theta d theta, like that. So it ends up working out pretty nicely. And you end up with the area to be equal to, and I'm going to put another dot, dot, dot here. I'm skipping this a little bit of steps here. And the area ends up being pi over 3. And that's the area of one loop of this rose curve right here. And we used tangents at the pole as we went through this problem. So that's kind of interesting to do. All right, let's see. The next problem I want to look at. Let's look at this cardioid. And let's do this problem. Let's look at the area. This is the cardioid. R is equal to 1 plus 2 cosine theta. And so let's look at the area of the inner loop of the, and I said cardioid, it's definitely not a cardioid, it's a limacon, the inner loop of the limacon. All right, so the inner loop of this limacon is this piece of the graph right here. That's what we're trying to find the area of. And so to do that, we need the tangents at the pole, because what we need here, the tangents at the pole are important for this kind of problem. And that's why I wanted to look at something like that, so you had some experience with that. You have to find this angle right here and this angle right here, because that's what the graph is doing. The graph, is coming in this way. This is our orientation of our graph, like this, and then it passes through the pole, and then it continues on like so. And so what happens to the graph is, what angle does it pass through the pole at? Those are the bounds on this on the inner loop right here. And so those are the angle values that we need here, definitely. And so how are we going to do this? Well, what are those angles right here? All right. So what are the tangents at the pole? All right, and I think this will probably be, I have another problem that I would like to work, but I'm going to probably save that one until the next time. So this will probably be to finish up the day, by the way, here. So tangents at the pole, we set r equal to 0. So we set r equal to 0, and we have 0 equals 1 plus 2 cosine theta. And I set up the numbers so that they work out relatively nice. We get cosine of theta equals -1/2. And so theta, cosine is equal to +1/2, remember, at pi over 3. So this would be the quadrant 2 version of pi over 3, which would be 2 pi over 3. Right? We know that the cosine of pi over, the cosine of pi over 3 is +1/2. That's right. So the cosine of 2 pi over 3, which is the quadrant 2 version, would be -1/2. And the quadrant 3 version would be at 4 pi over 3. So those are the angles I'm talking about right here. This is the angle theta equals 2 pi over 3 right here. So it passes through the pole at theta equals 2 pi over 3. And then you are, as the theta values proceed on from 2 pi over 3 to 4 pi over 3 right here, the r values are all negative right there. And that's why you're tracing out the loop on the other side of the pole there. It's because the r values are all negative in that interval right there. And so you're going from, again, so area could be set up this way. The integral from 2 pi over 3 to 4 pi over 3, like that. That's one way you could integrate. Let me clean up that limit of integration so it looks nicer. So this is 2 pi over 3 right here. Or you could do the integral from 2 pi over 3 to pi and multiply by 2, which is what I would prefer here because pi and 0 are easier to calculate than 2 pi over 3 and 4 pi over 3 and all that. So that's actually the one I'm going to use, is that second one. And I'm going to integrate then. So this is going to be, area is going to be 2 times the integral from 2 pi over 3 to pi, and this would be 1/2 times r squared, which is 1 plus 2 cosine theta quantity squared d theta. 1/2 r squared d theta. So the 2 and the 1/2 cancel. That's really nice. And so you're just integrating from 2 pi over 3 to pi, and this is 1 plus 4 cosine theta plus 4 cosine squared theta d theta. And once again, you're going to use your trig identity here for the square of the cosines. This is 1 plus 4 cosine theta plus 4 times 1 plus cosine of 2 theta over 2. And then this would be d theta. Kind of squeeze in the d theta there. And rather than going through all the horrid algebra there, I'm going to do one of my dot, dot, dot tricks here again. So in other words, fill in the details right here, and you get that the area is going to be pi minus 3/2 times the square root of 3. That's the area of that. And so I would want you to fill in the gaps there and see if you can fill those in and actually find that area like that. All right, so that's some good problems to look at for area bounded by a polar curve. And I'm probably going to finish with one more of those. This is going to be the problem I'm going to do. The curves here are r equals 4 sine of 2 theta and r equals 2. R equals 2 is my circle, and 4 sine of 2 theta is the 4-leafed or 4-looped rows. And I'm going to do this problem on Monday in lecture. I'm going to work in lecture on Monday. And what we're going to try to do here is we're going to try to find the area that is inside the both the circle and the, so we're going to find the area inside both the rows and the circle. Okay, so that area, you're talking about this region in here, right? This is one piece of it, at least, is this piece right here. So you're certainly welcome to try this problem. It's not something I'm going to pick up for a grade at all here, but something that I would want you to be able to get through this kind of problem, right? And finding these areas, we're trying to find the area of all 4 of these pieces. So obviously one thing you do is just find the area of one of these little sections, right? And that would be multiplied by 4, right? But it's kind of tricky as to how to find the area. And so that's what we'll talk about on Monday. So this is a Monday problem for us, okay? So the homework that is due Monday, not Sunday. Sunday is Easter, so I decided that I would not have homework due on Easter. So homework is due on Monday, and this is going to be April the 2nd. Hard to believe it's already April. And so in your textbook, this is on section 7.4 of your textbook. Simply 2 problems. This is problem number 236 in that section. And we will say problem 204. Those 2 problems are due on Monday rather. And please, again, I have no problems with you asking me for help. Even though it's Easter Sunday, I will be online Easter evening from 8:30 to 9:30, like always on Sunday. I also have office hours tomorrow from 11 to noon. So don't hesitate to stop by. I'll be in my online office. I'll be happy to help you out. Email me, that's great. Send me a remind message, that's great. I'll have no problems trying to help you out. All right, so hopefully you have a good evening. Please get started on